System Perspective by Ted Lewis. A system contains components, each with single asset risk. This risk is modeled by the simple risk equation, T times V times C. In a system, however, T times V is replaced by an exceedance probability, EP, and risk is defined as the product, EP times C. This equation is called the maximum probable loss, because it represents the maximum loss rather than the expected loss. For example, a 6.9 or greater earthquake in Northern California occurs about once in every 33 years. Earthquake loss is a system loss because it involves many components that make up civilization. In Northern California, that means freeways, power grids, water pipelines, homes and offices, and factories. These components are part of an interconnected system. Assuming the EP of a magnitude 6.9 earthquake is 3%, the probable maximum risk would be the product of this equation, $28 billion times 3%. Thus, the maximum probable loss is $848.5 million on an annual basis. Of course, a 6.9 magnitude earthquake does not occur every year in California. But if it is certain to happen at least once every 33 years, the probable maximum loss in each year is 1/33 of the 33-year maximum. The exceedance probability for a system catastrophe is actually a curve, not a single value. This curve relates the likelihood of an incident equal to or greater than a certain size or consequence. That is why it is called an exceedance. Recall that the bell curve is a normal distribution centered on an average value. Most of the time, incidents fall on or near the average value. As catastrophes deviate from this average, they become precipitously less likely. In fact, their likelihood essentially vanishes as incidents become both smaller and larger than the average. However, most catastrophes don't obey the normal distribution. In stark contrast to the bell curve, black swan events, normal accidents, and sand piles obey power laws. Black swan events possess radically different distributions in two major ways. First, they are lopsided, or what scientists call long-tailed. Second, there is no average value. That is correct. Power laws have no average value. There is no expected value for a black swan event. According to the power law, everyday incidents are small and frequent, but once in a long time, a rare and major incident occurs, the black swan event, and this event is so large and rare that it comes as a shocking surprise. Note that the black swan events are way out on the end of the long tail. The longer the tail, the bigger and more frequent the event. The long-tail power law distribution is significantly different than the bell curve in two important ways. First, probable events don't vanish as they do according to the bell curve. This means that the black swans are more likely to occur than we expect from using the bell curve. Hence, while extreme events are unlikely, we should not discount them entirely. In fact, they should not come as a complete surprise to us. The second important feature is this. As a system's self-organized criticality increases, its power law tail grows. That is, black swans become more frequent as the power law describing them gets longer. In fact, the tail goes on forever. For this reason, there is no average value. And without an average, there is no such thing as an expected outcome or consequence. Power laws do away with normality. Why do we care about this seemingly insignificant mathematical detail? Because the length of the power law's tail is directly related to the severity of the catastrophe. In fact, longer-tailed systems contain more self-organized tension and are therefore more likely to fail dramatically. The longer the tail, the bigger the crash. Now, this result seems to apply to size of consequences, the event's location in space, and the elapsed time since the previous event. What is fascinating about this theory is the observation that power law tails describe not only the likelihood of severity, but also the likelihood of the distance from the last catastrophe on the surface of the Earth and the elapsed time between catastrophes. While this observation does not hold in all cases, It does hold for some very important cases. We will discuss a few of these particular cases next. So much for theory. Consider the following system that represents a small piece of the global Internet. An Internet storm occurs when a zero-day virus goes on a rampage and spreads throughout the Internet. The virus duplicates itself and jumps from computer to adjacent computer. It can spread like a wildfire or disease. Here is an animation of the spread, along with an exceedance probability curve that relates the fraction of damaged computers to the consequences measured as number of damaged computers. Virus spreading is repeated over and over in this simulation. Note the green bar chart representing exceedance probability, and the jagged black line above the green bars representing maximum probable loss. The jagged loss curve rises and then falls with increasing consequence. Remember, here consequence is defined as the number of damaged computers. This system of computers simulates a randomly wired Internet. But the Internet is not randomly interconnected. Instead, the Internet is a type of scale-free network that possesses major hubs for countless connections and millions of computers with only a few connections. So, we need to try again. The Internet isn't a random network. It's actually very structured. It has a few big hubs, shown here as the dense areas of the example network, and many sparsely connected nodes, shown here around the circumference of the network. Scale-free means the network has a structure defined by a power law. A power law is a kind of fractal that looks the same at all scales. Magnify any piece of a power law, and you get another power law. Hence the self-similar fractal nature of power laws. Scale-free, self-similar, fractal, and power law are all different terms for the same thing. Note in this simulation that the exceedance probability is much longer and fatter. It is a fat-tailed power law. This means that the maximum probable loss risk is much higher for a scale-free network than the previous random network. In fact, the jagged black risk curve goes up with consequence and never returns. Risk gets worse with consequence. This leads us to our main point. Because the Internet is scale-free, it is more vulnerable to the spread of a virus than a random network because it has hubs. Now consider a type of network that behaves in the opposite fashion with respect to maximum probable risk. Here you see a clustered network. This network has many highly connected neighborhoods with only a small number of interconnection links between and among the neighborhoods. But unlike a scale-free network, a cluster network has no major hubs. As a result of clustering without major hubs, a contagious virus cannot spread very far or fast. This network is more resilient than either a scale-free or random network. Note how the jagged risk curve actually goes down as consequence goes up. So what did you just learn? First, systems behave much differently than single assets. Systems can be fragile or resilient, depending on their structure. Risk and resilience in a system depend on two things. 1, the vulnerability of individual components, and 2, the structure of their interdependencies or connections. Conversely, a system can be made more resilient and lower risk by eliminating structure. Remove or reduce hubs by reducing the number of links in the system and the size of the hubs. This is one form of self-organization that can be controlled to increase system resilience. The exceedance curve and maximum probable loss definition of risk apply to consequence. This means that they can relate the probability of an incident to its size. There is another important question to be asked. When will the next incident happen and where? This is where Paul Levy comes in. A levee flight or levee walk is a meandering in either time or space that takes different size steps, some large and some small, according to a power law. Levee walks consist of many small steps, a few medium-sized steps, and only a rare number of very large steps or leaps. So what? As it turns out, levee walk behavior has been observed in economics, spread of epidemics, Al-Qaeda attacks, and in nature. Both humans and animals forage, which is a form of levee walk. If we know the power law for levee walks, we can estimate when and where the next incident is likely to happen. This is the theory. Does it actually work? As a visualization, consider the cube shown here. It has 3 dimensions: location, time, and size. If we knew the space-time consequence box for hurricanes, terrorist attacks, or floods, we could estimate when and where the next major disaster is likely to occur and how big it might be. Is this really possible? Here is an example using known data on Al-Qaeda. Ever since the Al-Qaeda attacks on the United States in 1993, there have been a series of attacks around the globe with varying degrees of consequence. Our first step would be to plot these attacks as an exceedance probability curve, as shown here. When we do this, the attacks appear to follow a long-tailed power law distribution, almost like a perfectly charted textbook graph. This indicates that by far most attacks killed fewer than 100 people. The probability of a 9/11-sized attack is not 0, but very small. So small it doesn't even appear on this graph. Now, if we analyze the same data as a levee walk, we discover that the distance between subsequent attacks also follows a long-tailed distribution. This distribution is not as close to a power law as the consequence graph, but it still communicates valuable information. It says that most subsequent attacks are close to the previous attacks, as the crow flies. Finally, if we analyze the time interval between subsequent attacks, we will discover another long-tailed power law. This one appears to be almost as perfect as the consequence graph. The time graph is a levee walk in time because it matches a long-tailed power law. So we have a space-time consequence cube for Al-Qaeda attacks. Is it possible to predict when, where, and how big the next Al-Qaeda attack will be? Not exactly. But this kind of data analytics is a type of predictive analytics that can be used to significantly narrow down the search space for potential future attacks. Perhaps the most interesting result is that consequence, distance, and time are all levee walks. And levee walks are fractals, meaning that their patterns repeat in terms of space, time, and consequence. There is a third way to look at systems, using game theory. In this approach, we imagine that the attacker and defender are 2 people competing against one another. For example, the attacker might be a terrorist and the defender might be a city policeman. Or the attacker might be someone trying to blow up an airliner and the defender might be the TSA. The game works like this. The defender tries to minimize the risk and the attacker tries to maximize risk. This concept is called a Stackelberg, named after German economist Heinrich Stackelberg, who was the first person to study the idea of competing players. The boxes shown here sketch out how a Stackelberg game is played. First, the defender puts up defenses to minimize risk. Then the attacker probes the defense to find weaknesses and maximize risk. This process of defender-attacker moves repeats until a stalemate is reached. This stalemate is called the Nash Equilibrium, after the famous mathematician John Nash. The Cold War between the United States and former Soviet Union reached a stalemate. Both sides optimized their positions. The United States minimized its risk by deploying mobile missiles, and the USSR maximized risk by building more nuclear warheads than anyone else. In the end, the game reached an impasse. The advantage of this approach is that we do not have to estimate threat, T. Instead, we let the game begin inside of a computer. The computer calculates both T and V, because T maximizes the risk from the attacker point of view, and V minimizes the risk from the defender's point of view. We only need to know what the consequence is. Consider this simple example. The gray boxes contain estimates of T, V, and C before we play the Stackelberg game. The colorful boxes contain the results of calculating T, V, and C using Stackelberg. Here we assume the attacker allocates resources to increase threat T, and the defender allocates resources to reduce V and C. C reduction is achieved by improving response following a successful attack. Suppose there are 2 infrastructure targets, a bridge and a computer. Furthermore, assume the bridge has initial T, V, and C values of 5%, 100%, and $1,000, respectively. Similarly, suppose the computer T, V, and C values are 20%, 50%, and $1,000 initially. Also assume each player has $500 in resources to apply to maximization and minimization of risk. Now let's Stackelberg maximize the risk by adjusting the attacker's T values and minimize risk by adjusting the defender's V and C values. We assume each player has $500 to spend on resources. The attacker can spend some on overcoming the defender and vice versa. The defender can spend up to $500 on prevention and response. After iterating back and forth many times, a Nash equilibrium is reached with the following values of T, V, and C. For the bridge, we find that T increases from 5% to 78%. V decreases from 100% to 39%. And C decreases from $1,000 to $224. For the computer, T remains the same at 20%. V drops from 50% to 22%. But consequence remains unchanged because $0 were allocated to response. Note that T and V were calculated. The initial guess was revised by the game, becoming outputs rather than inputs. Stackelberg is not guaranteed to work in all cases. That is, some games do not reach a stalemate. Instead, they give mixed results. This leads to a mixed strategy game. No Nash equilibrium exists, but a mixed strategy does exist. This means that one strategy could be applied, say, 1/3 of the time, and another strategy is then applied 2/3 of the time. Mixed strategies are perhaps more common than stalemates. They have greater utility in the real world. Examples of mixed strategy game theory applications in Homeland Security are the Armor Protect, used by the U.S. Coast Guard, and GUARDS software, used by the TSA to allocate security resources in airports. These strategies use randomization to outwit terrorists. One of several strategies is selected every day at random, so the terrorist does not know which strategy is being deployed. The example here is a very simple illustration. In practice, there may be dozens of alternatives to choose from. Let's look a bit closer at the TSA GUARDS software. The game is played as follows. The attacker has an array of attack modes to choose from, maybe an IED attack, or perhaps a chemical attack at various locations throughout the airport. Similarly, there is a list of targets. Maybe one is the ticketing counter, and another is at the boarding gate. The defender has an array of defenses. Perhaps inspectors are placed at the luggage check-in, or passengers are required to submit to a pat-down, etc. Finally, the defender has a limited set of resources, people, inspection machines, etc. How should the defender use its limited resources? Strategy A. GUARDS uses a scoring technique to evaluate moves made by attacker and defender. Here you see one such move and counter move. If the defender uses its limited resources and defenses to block the attacker at 2 targets, you get the tactical moves shown here. Further, if the defender happens to select the same target that is attacked by the attacker, the defender receives an award. Ka-ching! Attacker gets 0 return on investment, defender is rewarded. Strategy B. But consider Strategy B, where the attacker successfully attacks an unprotected target. The defender allocated resources to the wrong target, so now the attacker scores a win. Ka-ching! Attacker wins and is rewarded. Defender is not. Strategy C. Finally, in this strategy, the defender blocks the attacker again, and so the defender is rewarded. Get it? Protect is called Protect because the defender is rewarded when it successfully protects passengers. The Protect software simulates these moves and finds the best mixed strategy that minimizes risk. In this example, Strategy A is played 0%, Strategy B is played 33%, and Strategy C 67% of the time. The TSA randomizes its strategies to keep the attacker off guard, but in the end, Strategy B is played 33% of the time and Strategy C the other 67% of the time. Before moving on, let us look at one more strategy, the layered defense strategy. Most people think this is the most effective way to use resources because the likelihood of passing through several security layers drops off exponentially. This simulation illustrates the idea. There are two players, red and blue. The red player tries to get through the layers established by the blue defender. Each blue layer is considered a porous membrane. That is, each is nearly secure but not perfect. Some red agents find holes in the layer and get through. But they have to get through several layers to successfully attack the target. The question is, how many imperfect porous layers are enough? Layers cost money, so we cannot add layer upon layer ad infinitum. Instead, we want to add just the right number of layers, keeping budget limitations in mind. Suppose the permeability of each security layer is 1 in 20. That means that only one red in 20 gets through, on average. How many layers do we need if we are willing to accept only 1 in a million red agents getting through all layers? As shown here, there is a diminishing return in adding more and more layers. Risk goes up with permeability, but is partially mediated by the number of layers. If permeability is 1 in 20, then 4 layers is about right for a 1 in a million failure rate. Adding more layers improves the odds, but is costly. There are many other models for studying risk and reducing threat, vulnerability, consequences, and exceedance probability. For example, agent-based simulations have been used to find gaps and unexpected surprise attack modes. The simulation shown here illustrates a very simple agent-based search simulation. These advanced methods are beyond the scope of this course. One more thing. Risk reduction is only one of several goals of critical infrastructure protection. Another goal might be to reduce risk in such a way that the money we spend on risk reduction has a high return on investment. For example, risk ROI might be defined as shown here. ROI equals initial risk minus reduced risk divided by cost of investment. Instead of trying to reduce all risk, this strategy tries to get as much risk reduction as possible while economically allocating investment dollars. For example, if the initial risk is $100 million and we can reduce it to $50 million by spending $1.5 million, the ROI is $33.33 per dollar invested. If the same $1.5 million is invested in some other asset that returns $80 per dollar invested, then it is wiser to invest in the higher ROI asset. Let me summarize. What is the least amount of information needed to make a risk-informed decision? As it turns out, the single asset model is easiest. Threat T can be obtained from intel, vulnerability V from a subject matter expert, and consequence C from economics. How much does it cost to repair, replace, or respond to the damages? What are the secondary costs? For example, the damages to the Twin Towers in 2001 were approximately $30 billion, but the secondary economic damages were perhaps as high as $500 billion. So, consequence estimation can vary depending on how you define consequences. The next most elaborate risk-informed decision-making process involves an analysis of a system of assets or components instead of single assets. In this case, we need more powerful methods, and exceedance probability is the simplest. Exceedance probability curves are obtained from a posteriori probability estimates, which are obtained from historical records. Finally, an even more elaborate approach leads to an examination of the structure of complex systems that are subject to cascade failures across sectors. These are often called complex catastrophes because they are massive failures like the 2003 blackout of the power grid or the massive Superstorm Sandy. To fully understand complex catastrophes, we need to dig deeper into the theory of self-organization, fractals, and complex interconnections among systems.